So we're going to look at attacking foundation, and the things you're going to look at basically the IP version 4 and IP version 6 header structure, and some of the weaknesses that exist within the IPs, that is version 4 and 6, that can be used to exploit the network. And then so we'll also look at the number of vulnerabilities that are associated with the IP version 4 and 6 that enable for network attacks. And lastly, we will look at the TCP and UDP protocols, which are very crucial. And most of the protocols are built on top of these two protocols, the TCP and UDP. And so we'll look at the vulnerabilities that are associated with the TCP and UDP. All right, so we'll begin with IP protocol data unit, the PDU details. I do understand that in my previous class, I went through this, but I'll link the link to that session here sometime later. It's not there right now, or I'll leave it in the comment section below. So IP version 4 and IP version 6, these protocols are not new to us. So right now, most of the places are migrating from IP version 4 to IP version 6, and I mean, we are bound to have existence of loopholes at the place where we are doing the migration, the transitioning. So that also creates room for attack surface. IP version 4 itself was not designed with security considerations, and so that opens a room for vulnerabilities. Yeah. So IP was designed as a layer 3 connectionless protocol, and just provides the necessary functions to deliver a packet from source to destination. And then it makes no effort at all to validate whether the source IP address contained in the packet actually came from the source or not, and therefore that one opens room for spoofing attacks. Yeah. And then another thing that can be done to IP headers is that the attackers can easily tamper with the header information or the header fields that carry out the attacks. Yeah. So that's why it's very important as a security analyst, or for us who are training to be one, to actually understand the structure of both IP version 4 and IP version 6. We really need to know what the headers contain and where the attackers can ingest data that they so wish to transfer across using the IP headers. So looking at IP version 4 header packet, so these are the fields. You can see it has a version, an internet header length. You can see it has a differentiated service.
Excuse you.
Yes.
Share screen.
Oh, you can't see the screen. Sorry. Oh,
yes.
I am fond of that. I hope you can see my screen right now. You're able to see?
Yes, it's
Great.
okay.
All right. Yes, so we have so these are the header fields of IP version 4. As I mentioned, we went through this some time back, but it's just good to know, since repetition is the mother of learning. And now that we're looking at IP's vulnerabilities, it's a nice thing to go through this again. So we have so when you look at it, it is 20 bytes. The size is like 20 bytes, and you can see it has a field for the version, so which contains actually just version 4 in form of bits. That should be something like 0100, because that is 4, and then the internet header length also in form of bits. It also has differentiated service, the differentiated service CP and ECN. It has the total length, it has the identification, the flag, the fragment, offset, time to live, protocol, and so one thing to also take into consideration is IP, bit IP version 4, right? IP version 6, all of those are found in layer 3. And layer 3 we said is the network layer, yeah, in the OSI model, if you can remember. And the function of that is just to ensure that packets are able to transfer from the source to the destination, yeah. So looking at the IP version 4 headers, I'll just pick them randomly and discuss them. So I said the version is basically tells us which version of IP this is. So if it is version 4, we'll have in bits we'll have 0100. If it's IP version 6, we'll have something like 0110. I'm just doing calculation of head, the bits calculation. If I'm wrong, you can correct me, but that should be the case. And then we have the internet header length, this one, the IHL. You can summarize it as IHL, the internet header length, and it's normally 4 bits. So what you can see, this is 1 byte. That means it's divided into 2 bits. So we have 4 bit here, 4 bit here. Yeah, because 8 bits form 1 byte, right? So the internet header length is 4 bit, the version is 4 bit. So, and what the internet header length does is it specifies the length of the IP version 4 header. So how long should the IP version 4 header be, which is in 32-bit words, yeah. So the minimum value of the IP version 4 header should be like I think like 5 bits, yeah. Yeah, so basically that is it, and there's some more information on that. Yeah, so the header can even go up to 60 bytes in terms of size. So it can be 20 bytes, 60 bytes, yeah, it just depends. So, and what's the importance of the internet header length? The importance of it is that most of the times it helps routers to determine the size of the header, and thus and also if it can determine the size of the header, then it can tell the beginning of the payload, yeah. And then we also have a type of service. So we have the DS differentiated service here. There we have the differentiated service CP and ECN. I think we have those defined down here. Yeah, diff service, differentiated service or diff service. And then the ECN is explicit congestion notification. Yeah, let me admit someone here. Okay, I thought someone was joining.
That must have been me. I got logged out.
Okay, that okay, sawa. Well, so we're looking at service type. So we have differentiated service, and we have explicit congestion notification, the ECN. Yeah, from so I just wanted to stick here. So basically these ones give us the type of service. It's just used to specify the quality of service desired for the packet. So it can indicate the priorities such as low delay, high throughput, and reliability. So this is type service. We can generalize everything here as type of service. And then we have the total length right here, which is, so type of service is normally like 8 bits. Yeah, it should be 8 bits. this one's saying 2 bytes. Don't know whether that should be the case, but anyways, so the total length, the total length right here, it is you can see 4 bytes by 4 bytes and 3 bytes. That should give us close to the 7 bytes in length. Well, so total length indicates the total number of the packets, including the header and the payload. So in most cases, you get that the maximum length is from the previous class. We said that the maximum length is 65,000 bytes, 65,500 and 35 bytes. So which allows for payloads up to around 65,535 bytes when the header is 20 bytes. So that is the total length. And then we have this section, the identification, and that's normally 16, in most cases 16 bits. Yeah, this is normally 16 bits, and it provides a unique identifier for the packet. So why do we need unique identifiers for the packets? That identifier is useful when we are doing reassembling of fragmented packets. Remember when packets, when you're transmitting packets, normally fragment the packets so that the packets take different routes, and then at the destination we have to do the reassembly of those packets again. So we use the unique identifiers to reassemble the packets back to the original, to reassemble the fragments into the original packet. Yeah. And then of course we have the flag, and it's somewhere like 3 bits. It has like 3 flags. The reserved bit, which must be 0, and then we have another flag, do not fragment, the do not fragment flag, and more fragments flag. Yeah. So, and what do these flags do? They just help to manage packet fragmentation and reassembly. So if we set the do not fragment flag on, that means we're not going to fragment that packet. We're not going to fragment it at all. It's going to be transmitted as it is. Yeah. If we set the flag to more fragments, then we can, I mean, yeah, that means that packet can be fragmented, or it's a fragment, something of the sort, but you can read more on that. So the flags just help in managing of packet fragmentation and reassembly at the end of the day. So you can see identification helps us to reassemble packets that have been fragmented, or in fragmenting packets we give them unique identification, and the same thing with the flag. Yeah. And then of course we have the offset, fragment offset. It's normally 13 bits, and this one specifies the position of the fragment in the original packet. Yeah. And it's measured in units of 8 bytes. Yeah. Also for reassembly reasons of the fragments. Yeah. And then we have time to live, the TTL, most of the times abbreviated as TTL. So the time to live, it gives us like a limit of the lifespan of the packet to prevent it from circulating indefinitely in the network. Yeah, if we don't have that, then that means the packet is going to circulate over and over in the network, and you can imagine what can happen. That one will result to packet congestion, traffic congestion, because we're not having packets dropped, and we're just having packets circulating aimlessly in the network without reaching their destination. Yeah. So we need to time our packets to ensure that we have efficiency in terms of packets moving from source to destination. And if a packet doesn't get to the destination, we drop that packet. Yeah. And a packet is dropped whenever its time to live, or TTL, expires. That means if it gets to 0. Yeah. So each time a packet gets to a router, the time is normally decremented. So before the packet leaves the source, we know the TTL is normally set to a certain value. So for example, give it a value of 10 at the source. So the first time it hits the first router along the way, while it is trying to seek its path to the destination. Of course, we know the number of routers it has to hop. So once it hits a router, its time to leave is normally decremented. So from 10 to be decremented by 1 to 9, like that. So if it hits like 11 routers along the way before getting to the destination, that means it will be dropped at router number, should be at router number 10 or thereabout, because its TTL will be less than the original set number, which is 10. It will have been decremented to 0, and therefore it means it will be dropped. So that's what basically happens along the way. And then we have of course we have so T time to leave. The next thing is the protocol. The protocol is normally like 8 bits, and this one just identifies the protocol of the payload, because we understand that the header information can carry a payload for different protocols. For example, it can identify a protocol like TCP, like UDP, like ICMP, and so on and so forth. You understand that we have so many protocols. Yeah, so protocol carries the protocol information, which allows the receiving host to know how to process the payload. Yeah, because if we don't have a protocol information, then it becomes difficult to process the information, yeah, at the destination. And then we have the header checksum, which is normally like 16 bits. So the header checksum, what it does, it provides a checksum for the header only. Yeah, and routers can use the header checksum to detect errors in the header, if the header has got any errors or not. Yeah, so if the checksum does not match upon arrival at the destination, the packet is normally discarded. Yeah, that means at the source we have to provide some source of it can like let me put it like, it can be like a hash value for that header, for the header information, and for at the source, and this information is normally like sent to the destination before any, I think should be before the packet arrives. So when the packet arrives, we expect it to arrive with a certain checksum. Yeah, so if we check the checksum and we realize that it doesn't match, then it means that this packet has been compromised, most probably along the way, and it's a wrong one, so it has to be dropped. Yes, and I think this checksum is normally sent on like three-way handshake, something of the sort. Wait a minute, three-way handshake, not really, but it is normally sent before the packet is sent. So yeah, and then you have source IP address and destination IP address, which I don't think we really need to waste time there. Source IP is for the IP where the packet originates, and the destination is where the packet is heading to. And I think we have discussed all this, and yeah, and then we have the options and padding. I think I skipped that. This is a field that varies in length from 0 to multiple of 32 bits. So if we have any option values, so if the option values are not a multiple of 32, zeros are added or padded to ensure that the field contains a multiple of 32 bits or something of the sort. So I missed that one. And then, so that was for IP version 4. Then we also have for IP version 6, which is, you can see IP version 4 has got quite a lot of fields. IP version 6 has less fields, but what is common is the source IP and destination IP are more or less it's the same. The version also is does the same thing. And then we have what we call the traffic class. So the version will indicate the version of the IP, that is version 6. The traffic class, which is normally like 8 bits, and that will that replaces the IP version 4 type of service. Remember, in IP version 4 we had type of service. So instead of having all of that, we have traffic class, which what does it do? So it has a differentiated service code point, the DSCP, and for quality of service, which is a QoS purpose, and explicit congestion notification ECN that we looked at, yeah, for signaling network congestion. So if you have network congestion, we need the ECN to signify that there exists network congestion. And then of course we have flow label right here, which is 20 bits. It's a new thing in IP version 6, and this field is used for real-time applications for signal routers to keep packets on the same path. Yeah, and that means it is basically preventing reordering of packets. Yeah, so that packets can flow in an ordered manner. So it's particularly used in prioritizing delivery of real-time data like voice and video. Yeah. And then we have the payload length down here, and what the payload, it is 16 bits. It indicates the length of the IP version 6 payload. Yeah. And that includes the extension headers and upper layer protocol data unit, the PDU. If you remember, we talked of the jumbo payloads. And those ones are normally handled differently, so maybe you can figure out how. We have a next header here. So the next header, similar to IP version 4 protocol field, and what it does is it indicates the type of the first extension header if it is present. Yeah. Hop limit is like the TTL, the time to live, and I explained what that does in IP version 4. Basically, it it's that value that decrements once a packet hits or hops or gets to a router. We decrement it by one to ensure that the packet does not circulate in the network forever, resulting to congestion. Because if you have each and every packet circulating over and over, then we're going to congest the route, right? Right. Source and IP, you know what those do, and I will skip those. And then we also can see that IP version 6 headers also contain extension headers, the EH, which provide optional network layer information. Then the extension headers are optional and are placed between the IP version 6 header and the payload. I think we also had, in IP version 4, we had options field, and I think it is similar to the extension header for IP version 6. It should be similar thing to the options in IP version 4. So what are some of the vulnerabilities after we've looked at in details? We've looked at what the IP version 4 fields look like and IP version 6, and then we need to have a clear picture of what sort of vulnerabilities can be used against the IPs, both version 4 and version 6. So we have what we call ICMP attacks, the DDoS attacks, address spoofing attacks, and the man in the middle, and we also have session hijacking. And most of these attacks, I think we have covered them before, but just to go through them briefly, is that the ICMP, which is the Internet Control Message Protocol, if you can remember, that we use to, help us, communicate whether we have errors and whether we have success and so on and so forth, sometimes can be misused. Yeah. For example, it can be misused when we are doing the ping. Yeah. To discover subnets and hosts on a protected network. So bad guys can use ICMP to basically get to understand your network architecture, not only architecture, to also discover if we have subnets and to discover if we have hosts on a protected network, if we have hosts which are up or down and so on and so forth. Yeah, and I think we'll be looking at that in details. So with the ping, we can use the ping or the echo packets to generate denial of service flood attacks, because you can generate, so if ping is not disabled in your network, what happens is the bad guys can use ping to generate lots of denial of service attacks by sending so many ping requests, yeah, to your network, to your network devices or hosts. And that means that your hosts get overwhelmed with the ping requests, and then of course they crash. Yeah. So we've looked at the denial of service and how that can be achieved through use of ping. And then we have the distributed denial of service, which is of course you use a number of you use a number similar to DOS, but now we have a coordinated attack from multiple sources. Yeah, so multiple sources sent the ping request, for example, or do the denial of service attack at the same time. So you get that your network is being attacked from a number of sources and not just from one source. So that becomes DDoS. And then we have address spoofing attack, and that means just masking the bad guys or the malicious persons or the malicious host IP with the legitimate IP in a network. So that way, that IP is that host is trusted because it is using an IP that is known within, or the IP that is trusted in the network. But under the hood, the real IP is not one that belongs to that network, or one that should be trusted. Yeah, and that way the bad guy is able to circumvent the security walls and access resources that's not supposed to access in the network. Yeah, and so this can be done to perform what you call blind spoofing or non-blind spoofing, and I think we'll be looking at the two, what the difference is. And then you have man-in-the-middle attack, of course, and what happens is that the malicious person just inserts self in between communication, and then and it's able to like monitor, capture, and control communication. Yeah, while eavesdropping at the same time. Session hijacking. So the threat actor gains access to physical network and then use the man-in-the-middle attack to hijack a session. Okay, so those are some of the attacks that can be done using the IP, some of the IP vulnerabilities. So what is ICMP attack? Now we're looking at those in details because we just mentioned. So as you can see, we have the attacker right here who is sending an ICMP echo request or a ping request to the victim. Yeah, and sending so many requests, and the victim has to reply to all those requests. So this one constitutes DDoS attack, a denial of service attack. If we have an attacker who has got a number of, let's say, other bots, is using bots to send ping requests to, or zombies to send requests to the victim, and all those are like coordinated sort of requests sent at a go in huge numbers that the victim can't access, then that is referred to as a DDoS. Yeah, so the following table we can see some common ICMP messages of interest. So there are different messages that can be sent using ICMP. So we have ICMP echo request and echo reply. So this one is used to perform host verification. Most of the times, the good use on the good side is we network administrators need that to perform whether a host is up or down. But at the same time, their bad guys will use it to verify whether also a host is up, and then do the DDoS. ICMP unreachable, which is used to perform network reconnaissance and scanning attacks. Yeah. So when you get this ICMP unreachable message, then that means the host is down, or maybe most of the times ICMP is disabled, something of the sort. So if you are scanning a network, then you use this to tell whether to tell which targets you would want to hit that are up and which ones are down. You shouldn't waste time. And then we have ICMP mask reply, and this one is used to map an internal IP network. And to get a map of the internal IP network, you can use the ICMP mask reply. And then we have ICMP redirects, which is used to lure a target host into sending all traffic through compromised device or man in the middle attack. So it's just a form of redirecting traffic to the bad guy, so that it doesn't get directly to the intended host, but it goes through the bad guy, and and then we have ICMP router discovery, and this one is just used to inject bogus route entries into the routing table. Yeah, remember we talked of routing tables some time back, so we can use ICMP to tamper with the routing table through the ICMP router discovery. All right. We also have what called amplification attacks. So the bad actor here has simply done IP, for example, IP has masked himself with the IP address of a legit host, who is the victim in this case. So he sends a request to some source, and then that source replies to the request in. Okay, so what happens here is, let's see. So this is amplification and reflection attacks. Most of the times they work together. To amplify something is to like increase the volume of. To amplify is to increase the volume. Yeah. So in form of request, we send one request, but we get a number of increased responses. Yeah, from a number of you can see from a number of sources here, they are all replying at the same time, and all the reply is directed to the victim and not to the source of the request. And why is that the case? Because the threat actor at this point is using the IP information of the victim. So when he's sending the request, but when is receiving the response, all the response is sent to the victim and not back to the threat actor. And the response is in huge volume. As you can see, it's a reflection, but then it is being amplified, and all that response hits the victim, and the victim is unable to handle all this response, and therefore it means it basically crashes. Okay, so we call this a smurf attack, which is normally used to overwhelm the target host. So amplification in the sense that the threat actor forwards ICMP echo request messages to many hosts. Yeah, many hosts somewhere in the network. Yeah, so it's those requests, and the message contained in the IP header address has the IP address of the victim. So all the reply will go back to the victim and not to the threat actor, because the threat actor has modified the header information to ensure that all the replies get back to the victim and not back to the threat actor. So a reflection in the sense that the replies don't go back to the threat actor but go to the victim. So they are reflected, all of them, to the victim. So we call it a smurf attack or amplification and reflection attack. I hope you make sense out of this. So we have other forms of amplification and reflection attacks. It can be in form of DNS-based reflection and amplification attack. It can also be in form of a network time protocol amplification attacks. Yeah, so it can be used in a number of protocols, just besides use of IP alone. And then we have address spoofing attacks, and so as I mentioned before, it's just masking of the IP address of the attacker or the malicious guy with legit IP address of a host in the network. Yeah, so so we use spoofing attack, which is normally incorporated into another attack, such as the smurf attack. So we said before that spoofing attacks can be in two forms: non-blind spoofing and blind spoofing. Of course, blind spoofing, the threat actor cannot see the traffic that is being sent. Yeah, so an example can be, it can be used in a DOS attack, but in a blind spoofing, the attacker, of course, is able to see the traffic. Yeah, so in a man-in-the-middle sort of attack. Yeah, so you can be able to see the attack that's being sent between the host and the target. and therefore we call it non-blind spoofing. So the attacker can inspect and reply to packets whenever need be. Okay, so that was IP address spoofing attack, and then we have MAC address spoofing attack, which is just now instead of the IP address, it's the MAC address, but the idea is more or less the same. So in this case, the threat actor will alter the MAC address and not the IP address. Yeah, we'll just mask it with the legit MAC address of some device. In this case, you can see the threat actor takes the MAC address of the server. Yeah, so instead of us having communication being sent to the server, it's being sent to the to the threat actor, because it's the one owning the MAC address. And we use MAC address and IP addresses for identification and communication in a network. They are two very important addresses in a network. Yeah, so that is it. Okay. So amplifications or service spoofing is another spoofing example, and a threat actor can connect to a rogue DHCP server to create a man-in-the-middle attack just by doing the MAC address spoofing. So let's look at some of the common vulnerabilities that exist in TCP and UDP vulnerabilities. I said these are two very important protocols that we use. Remember, if we need reliable communication, we use TCP. If we don't need reliable communication but faster communication, we use UDP. And we looked at these two protocols some time back. So what are some of the vulnerabilities that can coexist within these protocols? So first of all, we have to look at also the detailed information of these protocols, like the TCP segment header, because the TCP has got some header information. So the fields we can see it has a source port, and of course it also the TCP also needs to have a destination port. It has what we call a sequence number and acknowledgement number. It has a header, reserved, control bits, window, agent, checksum, and options. And I think we also looked at this some time back, but it will do us no harm looking at this again, just to remind ourselves. So the TCP segment information always appears immediately after the IP header. So we have the IP header and its fields at the top, and then after that we have the TCP. So the agent pointer field just tells us whether this packet is it significant or not, should it be transmitted immediately and stuff, given a sort of urgency or not. Acknowledgement is that field is used to tell us when we receive the packet, we have to acknowledge and something of the sort. And then we have the push PSH for push function, RST for reset connection, SYN for synchronized sequence number, and then fin for finished. We are done with sending the data, so we send the fin flag. So these are the 6 control bits of a TCP segment. Yeah. So if you asked of the control bits, so these are the ones: the agent, the acknowledge, the push, the reset, the sync, and the finish. Okay. So I said TCP is a reliable protocol delivery, reliable delivery. So that means if you are sending packets and some of the packets are dropped along the way, what happens is we resend again the packets that have been dropped. And for that matter, we say it is reliable because we're not losing any packets along the way at the end of the day. So some of the protocols that require reliability or that are built on top of TCP, we have protocols like HTTP, I think also HTTPS, SSL, TLS, FTP, DNS, DNS zone transfer, and so on and so forth. But not all forms of FTP. You also understand that we have TFTP that uses UDP, right? Flow control. So TCP implements flow control to address this issue. So rather than acknowledge one segment at a time, multiple segments can be acknowledged with a single acknowledgement segment. Yeah. And then we have stateful communication. So this is some sort of stateful communication between two parties during the TCP three-way handshake, right? So before data can be transferred using TCP, we need to have in place a three-way handshake to open the connection. Yeah. And then it's not stateless like UDP, where we don't need the three-way handshake. So by the fact that we have TCP three-way handshake, that ensures that the communication is stateful. Yeah, so the three-way handshake, as you can see, first of all, there is before communication begins, we have to establish the communication, and what normally happens is we have some sort of client-server communication session where the client will send a SYN packet to the server. The server will reply. If the server is up and ready, it will reply with SYN acknowledgement to say it's ready to communicate, and then the client will reply with an acknowledgement to tell the server that, okay, let's establish communication, because it's also available and ready for communication, and at that point communication is established. So that's why we call it a three-way handshake, as you can see. Yes, this also was a class some time back, and I think I will record that video sometime later and also upload it, so that in case there is anyone who wants to refer back to this, can easily do that. We have the TCP attacks, now that we understand the TCP three-way handshake, and that can be used by the malicious person or the threat actors to launch attacks. So we have what we call TCP SYN flood attack, where the TCP SYN flood attack is where so it exploits the three-way handshake, and the threat actor, what the threat actor does is continuously sends TCP SYN session request packets with randomly spoofed IP addresses. So there is some sort of scripting and automation of generation of spoofed IP addresses, and all those IP addresses are used to send TCP SYN sessions, yeah, to a web server, for example, as you can see in the image. And then so the target with the TCP SYN acknowledgement TCP SYN ACK packet to the spoofed IP address. So the target replies with TCP SYN. So you can see the web server is replying with the TCP SYN acknowledgement packet to the spoofed IP address. In this case, the spoofed IP address is one for the victim. So the victim receives a SYN acknowledgement of a packet that it did not send its SYN request. So it's receiving responses that it did not send any request for. Yeah. So you can see this sort of attack just overwhelms the victim. So the victim will try to send an acknowledgement to this web server, but so those requests the server will be unavailable, because it's trying to communicate to a server that it doesn't exist, and so the target host has too many half-open TCP connection, and the TCP services are denied to legitimate users. Yeah. So once the victim replies, then all the replies, the request, the SYN. So I think I'm confusing you here. So the victim who needs to send legit request to the server is denied access because the server has been overwhelmed by so many SYN requests already from the threat actor. So the threat actor sent so many SYN requests, and then the web server is busy replying to those SYN requests with the SYN ACK. And now the legit user who is supposed to send the legit SYN request to the server is denied access because the server is too busy replying to the SYN request of the threat actor. So that's what's happening here, and that's why we call it a TCP SYN flood attack. I think that explanation kind of clears the air here. And then we have the TCP reset attack, and what happens here is so a reset attack can be used to terminate TCP connections between two hosts. So a threat actor could do a TCP reset attack and send a spoofed packet containing TCP reset to one or both points. So so once you send a TCP fin, once it is received, TCP fin means finished. It means that you want to stop communication. So what happens if a legit host is communicating to the server, for example, right? And so what happened next during the communication? The threat actor gets to spoof one of those hosts, and for the sake of terminating communication, while while host node A was talking to B, and abruptly node B receives a fin that node A did not send, but one that was spoofed and sent by the threat actor. So that closes the communication immediately. So that can be used as a way of kicking out nodes from communication in a network. So you get that all of a sudden some nodes are kicked out of unexpectedly kicked out of communication. Yeah, and the threat actor can do that to free up space so that it can be gets the attention in terms of bandwidth and whatnot in a network. So that's a good way to, I hope that explains this. I could go through this, but I don't want to. Sometimes you wonder, how does one kick people out of a network? You can use TCP reset attack to kick people out of a network, especially if they were in a session. And then there's what you call session hijacking. And what session hijacking is, it's another form of TCP vulnerability where a threat actor takes over an already authenticated host as it communicates in a network. So you have a host that's been authenticated by a server that's in communication, and if the host is vulnerable and has been attacked, so the attacker takes over the session because it's able to get the keys to the session that will validate the attacker, and the attacker takes over the communication instead. Yeah. But the attacker must spoof the IP address of the host, and also predict the next sequence number, and then an acknowledgement to the other host. Yeah. So that is TCP. What about UDP? So UDP, which is used for the DNS, which is a very important segment of the internet. So it powers the internet communication, the DNS. So DNS uses UDP. We have DHCP also, TFTP as I mentioned before, NFS, and SNMP. All of those use UDP protocol. They are built on top of UDP protocol. And it's also used with the real-time applications that need to communicate in real time. And so such applications are like media streaming of voice and video. Yeah, all those use UDP. And we said that before that UDP is not not stateful. It is stateless. It's connectionless oriented transport layer protocol, and that means it doesn't really care whether you're losing or you're dropping packets along there or not. But what happens is the few packets you get at the end of the day or at the destination, make good use of those, because yeah, that's just it. Yeah, we don't really go back to check if there is any packet that was dropped along the way or not. Yeah, so we say we can, it is UDP is not secure, but you can build some security around UDP. And we say that although UDP is normally called unreliable, doesn't mean that the application that use UDP are always unreliable. It means that these functions are not provided by the transport layer protocol. Yeah, and you can implement them as an additional layer somewhere else. You can see that the UDP has got lesser fields. The size also of UDP is less compared to that of the UDP headers. It's the size of the UDP header is less compared to the TCP header. That means it is lightweight, yeah, and with the low overhead header information, makes it very desirable for protocols that make simpler request and reply transactions. That's what gives those protocols the speed they have and enable them to do voice over internet or transmit video and so on and so forth, and files. Yeah. So some of the attacks. So when you look at this information, it is so simple. I mean, source IP, destination IP, the length, the size, and the checksum, just to check the ensure that the header the header that was sent is exactly the one that is received at the destination. So what are some of the attacks? So you can see that UDP is not protected by any encryption, but you can implement encryption on top as an additional layer. So by the fact that it lacks encryption, it means that anyone can be able to see the traffic. So we have what we call UDP flood attacks. So and that means that all the resources on a network are consumed because of the UDP requests here. So the threat actor must use a tool like UDP Unicorn or low orbit ion cannon to send UDP requests. Yeah. So these tools are capable of sending flood of UDP packets, often from a spoofed host, to a server on the subnet. And then the program will sweep through all the known ports, trying to find closed ports. This will cause the server to reply with ICMP port unreachable messages. Yeah, and then so since we have so many closed ports on the server, this creates a lot of traffic on the segment, which uses up most of the bandwidth, resulting to a similar thing like a denial of service attack. Yeah. And I think that marks the end of this module. So briefly what we looked at the IP, and we said that it is a layer 3 protocol. And then we have IP version 2. We also looked at in details at the header information of IP version 4 and IP version 6 and how they differ, and the similarities between the two. And we looked at some of the common attacks that can be leveraged on IP version 4 and IP version 6, and we looked at attacks such as ICMP attacks, denial of service attacks, DDoS, address spoofing, and man in the middle and session hijacking attacks. And then we also looked at ICMP, which was developed mainly to carry diagnostic messages used mostly by network administrators to diagnose their network. So the ICMP also can be leveraged by the bad guys to attack the network. We also looked at TCP and UDP information headers, what was contained in there, and some of the attacks that can be leveraged on TCP and UDP, like TCP port scans, TCP SYN flood attacks, TCP reset attack, TCP session hijacking attacks, and so on and so forth. Yeah. So that marks the end of this module. Until another day, just want to say thank you. Is there any question? Okay. If there is none, then we call it a day. Thanks.